different types of technology and team-based learning affects overall student learning, because Top Hat and TBLs were not always a part with these courses. So one of the things I'm going to start doing is I'm going to collect some data and do a little bit of analysis to understand a little bit about the differences in overall student performance, overall student perceptions, on the use of digital teaching interfaces and team-based learning within the large lecture biomedical courses. None of the data is going to be analyzed until final grades are in, and I'm not actually going to see names associated with any of the data that I get back. So what is actually going to be passed around is a consent form. It is entirely up to you if you want to participate or not. You don't have to. It's really just going to be overall averages of team-based learning grades, exam performance, and a survey that I would send out for people to answer if you agree to participate. All the data that I have in my regular spreadsheet will be anonymized, then it will be sent to Corey. So he won't see anybody's names associated with their grades. I will anonymize it first, then he's going to rearrange everything and anonymize it again so that when I get it back, I have no idea whose grades are whose. Okay, so that way everybody's data is going to be completely anonymous in terms of how I'm actually going to use it for statistical analysis. Okay? So that's what's coming around. You don't have to participate. I would obviously very much appreciate it if you did. But if you decide not to, that's how I'm going to set up the spreadsheet that I send to him to be anonymized, so that only the people who have signed the consent form will be included, will have their data included. And they will also be the only ones that have responded to the actual survey when I sent it out later on this semester. Anybody have any questions? Okay. Alrighty. So let's get back to our non-functioning projector system here. Let's see if at least you can see it on here. I hope there's not a glare. I'm sure there will be. But let's try. Yeah, we'll go with glare. All right. Unfortunately, this is the best I can do until this starts working normally. All right, so the last thing that we left off at was talking about our PD loop. Okay? And we were talking about the PD loop. We walked through exactly what's happening at each point. How did we come up with the PD loop? Where did we get all the information, the data points to actually make this loop? Yeah.
It's like a replotting of the Wiggers diagram.
Yes, that Wiggers diagram or the cardiac cycle diagram that we saw before, that had that really massive one, that is basically the same thing here. The difference is, instead of looking at how pressure changes over a time course and how volume changes over a time course, we're looking at how pressure changes in response to different points in volume. So starting at point A, we have the lowest volume on the x-axis and also the lowest pressure. Okay, so what state is the ventricular muscle in right now? Contracted or relaxed? Down at point A. Relaxed, right? You are completely relaxed. Everything is at its lowest point. Lowest amount. Oh, sorry, that just went to sleep. Lowest amount of pressure and lowest amount of volume. So, what happens at that point as you are beginning to start allowing volume to increase from point A to point C? What happens at point A? The valve is going to open. Which one? Atrioventricular or semilunar? Atrioventricular. Okay, in this case we're looking at the left ventricle, so we're talking about the mitral valve. So the mitral valve is going to open at point A, and you have that rapid filling from A to B, followed by the reduced filling from B to C. What is happening in this little blip right here? That bulge is a bulge in, well, this is looking at that little bit of pressure, but That blip in pressure for that final increase corresponds to what part of the cardiac cycle? Atrial contraction. Okay, so you're finishing filling it up. At point C, you have now hit that point where ventricular pressure is higher than atrial pressure. You filled it up, enough pressure is generated that your mitral valve is going to close, and now you start systoling. Okay? Same exact volume, no change in volume. The only thing that's happening from C to D is that you are going up in pressure. That's your isovolumetric contraction, followed by what happening at point D? Ejection. Okay? So if you're going to eject, that's starting at point D. What has to happen? Aortic valve has to open, right? So your semilunar valve is opening up, which means your blood inside all of that pressure now has a way to get out. So you have a rapid decrease from D to E in overall volume. You lose 2/3 of it in that D to E portion. And you will have a slight increase in pressure. Why does that happen?
Contraction of the ventricle makes the volume inside it smaller, so there's more fluid in there, and then going through that semilunar opening, so there's going to be more pressure on the walls as well.
There'll be a little bit more pressure on the walls because you're going from a big cavern to a little hole. Okay, it's like going from an underground cave through a tunnel to get out. So you're going to generate a little bit more pressure as you are continuing to compress that blood. You're squeezing it even harder. Your contraction of those ventricular muscle cells is going to increase, and you're forcing out that volume, so you're going to have an increase in pressure and a decrease in volume. When you get from E to F, you start to see a drop off in pressure because you're almost at the baseline of your volume. You're almost done ejecting the blood. Point F, what's happening there?
Aortic valve closes.
Aortic valve closes. Okay, why?
Pressure is less.
Pressure is less than what? Less where? Where is it lower? In the ventricle, compared to the aorta. Okay, remember that the aorta is going to hold on to a little bit of blood on the other side of that wall, so you're still going to have a much higher pressure. And once the ventricular pressure drops below the aortic pressure, the aortic valve is going to close, and now you are going to start the isovolumetric relaxation. Okay, and then that will bring us back down to that initial start point. Oh yeah, so I'm projecting here instead of here. It was flipping out back and forth, so I don't know what's going on. I think it's it shows on, this is the website's looking fine, everything here is looking fine, but it'll show for a second, then it's right here. All right, so, if we can, yeah, just like, that's fine. Most of them have access to this on their devices too. Okay, so here I want to do a quick run through of preload versus afterload. Those of you who did 503 should recognize this figure, but now we're going to talk about it in the context of cardiac muscle. So, what, by definition, what point in that PD loop is going to be resting? Complete resting. No tension or anything on your cardiac muscle at all. Right before you start filling. Okay? Remember when you talk about tension that's developed by a muscle, it can be because of contraction, but it can also be because it's being stretched. Okay? So at resting, which is number A here, it's also point A on that PD loop. It's that point just before your mitral valve opens up, your ventricular muscle is completely relaxed, and it's not being stretched. All right? B is talking about when the preload has been added. Okay? When we're talking about preload specifically refers to a weight that is because that muscle is at rest, so it's not actively contracting, but it is being stretched. So at what point on your PD loop would that be? C, right? You're not contracting yet, but you're completely stretched. So right before you start to get any kind of systole, You have everything filling up the ventricle. It's at its maximum point. Yeah. And I'll talk about afterload in just a second. But your preload is right at the end of ventricular filling. The next one on that figure is preload plus afterload, but both of those weights are still resting on the platform. All right, so at this point, we're looking at here. So it's starting to contract, and it's still stretched. So at what point do we have any adding of the afterload without any additional stretch? You've already stretched to the maximum when we looked at the preload. So your preload is your end diastolic volume. It's the maximum amount that you can stretch that muscle. Now you've started to contract and you've generated that systole, but you haven't overcome the weight yet. Okay? If you haven't overcome the weight, it's this equivalent of saying you haven't quite picked up whatever it is you're trying to pick up. What is that equivalent in terms of cardiac function? Isovolumetric contraction. And when does this point stop before you get to the second one? D. Right? Because you haven't quite started ejection. So in this case, lifting of that afterload is equivalent to ejection of that blood. So C on this preload versus afterload figure shows your preload and your afterload. So it's stretched, it's also contracted, but it's still being supported. So you haven't overcome that afterload yet, which means you haven't gotten the pressure high enough to open that aortic valve. So it's just before the aortic valve opens, that's point C. And what is the contracted one? D to F. That's your contraction. You've overcome the afterload. The afterload, by definition, is that pressure that has to be overcome, or that force that has to be overcome in order to get contraction and ejection of that blood. So if you're talking about regular muscle, afterload is the weight that you have to overcome in order to be able to lift that weight. But for cardiac muscle, it's effectively the pressure on the aortic side, right on the other side of the aortic valve. That is the force you have to overcome to get blood out of the ventricle. So that's your afterload. So your preload is your end diastolic volume. The maximum amount that you're stretched, that's that stretching load force. And the afterload is the force against which you have to contract in order to get blood out, which would be your aortic pressure. Okay? So, resting, point A on your PV loop. Resting and stretched is point C. Contracted and stretched is point D. It's right at D, right before you open that valve, because you are at your contracted state and your stretched state. And then from D all the way to F, after you've overcome and are able to eject that blood, it's the span of that systolic ejection phase. Okay? Okay. We're going to have to continue this. Apparently there's a piece of equipment on the projection system that's broken, so they're bringing that in to fix. So I hope you guys can see okay up here. Can you see okay? It's not too much of a glare? Okay, yeah. Oh, you can see. Okay, thank you. I saw hands up and I didn't see the thumbs up, so. Okay, all right, so what happens to the PV loop if you're looking at left ventricular heart failure? First of all, if we're looking at left ventricular heart failure, the left side of your heart is not functioning at its full capacity. It's starting to fail, which means it can't generate the same force of contraction. That's called a loss of inotropy. So that word will be up on there a little bit later. But when you lose, I guess it is right now, loss of inotropy on the right. If you lose that contractile force, what does that mean for the blood that's in the left ventricle trying to get to the body?
You can't generate enough force to overcome the aortic pressure, and so it stays in the ventricle.
You have more of it staying inside the ventricle. You can't eject as much. That's what's happening on the right-hand side. So as a quick recap, over here on the left, this is your standard PV loop in a normal heart. This is your end systolic pressure volume relationship, which by definition is what? What? Anybody remember?
Is it the highest ratio of the work that's being done?
So yes, in a manner of speaking, it is. It's the maximum pressure that's generated, that the heart is capable of generating at any given volume. So at any volume value, this is the maximum pressure that this heart can generate. Okay? Your end diastolic pressure volume relationship shows you how capable it is of being stretched. At some point, it's going to curve up and then it's going to stop because you actually can't physically fit any more blood into that chamber. Okay? SV, anybody know what SV stands for? Stroke volume. Okay? If EDV, on the right, is your end diastolic volume. If EDV is your end diastolic volume, all right, well, I'll work on it. If EDV is your end diastolic volume, and your ESV is your end systolic volume, at the end of diastole, you are maximally filled. At the end of systole, you are as empty as you're going to get. Okay? So by definition, EDV minus ESV is going to be your stroke volume. Okay? That means for every single heartbeat, this SV here is the volume of blood that is going to be ejected from the ventricle. With me so far? Okay. So when we're looking on the right, the yellow loop is your control loop. That's basically what's going on in the normal heart. The red heart is showing what's happening in left ventricular heart failure. The biggest point here is the change in this ESPDR, this end systolic pressure volume relationship. What do you notice about the slope? It's decreased. Why is it decreased?
That loss of contractile force.
If you can't generate the sufficient contractile force, you can't ramp up the pressure to the same level that you could in a healthy heart. So for every single volume point, a lower pressure is capable of being generated. You can't get higher than that. Because that ESPVR can never be passed, because by definition it's the maximum pressure that can be generated at a given volume, your PV loop is never going to go over the top of that line. So if you lose contractile force, so loss of inotropy causes that slope to decrease, which is going to shift your PV loop. The first part that you've already mentioned is that you have more residual volume after contraction, which by definition is which parameter? What parameter is this?
Oh, EDV.
It's your ESV, right? The left side of that red curve, that red loop, that is your end systolic volume. That's the lowest volume that you can get under conditions of LV failure. Okay? So instead of, what, about 50 mils, now we're looking at 100 mils. If contractile force were the only issue, you kind of stop here. When you have left ventricular heart failure, your body's going to try and compensate for the fact that it can't get all that blood out. So what's it going to do? Blood's still coming back. Part of it's going to increase your heart rate, but in terms of the actual muscle itself. What else changed?
The end diastolic.
The end diastolic volume. It's going to stretch to be able to accommodate more. You're also going to have a thickening of that wall as you add more muscle cells trying to increase that contractile force. So you're going to end up with an enlarged heart. Okay, so your PV loop here is not only shifted over to the right because your end systolic volume is higher. The heart is not capable of pumping out as much blood to get all the way down to what is normal. A compensatory mechanism to try and maintain stroke volume is to allow it to stretch and accommodate more blood. So you end up with a little bit higher end diastolic volume. The problem is that compensatory mechanism is insufficient to meet the change in end systolic volume. So the stroke volume in the red here is smaller than the stroke volume in the yellow. Oh, sorry. Okay, you guys see how it's a little bit thinner? So the loss of inotropy is cause for the elevated ESV. The elevated EDV is a compensatory mechanism because the heart is trying to maintain that same level of blood that is leaving on every single beat. How do you feel so far? Pretty good? Any questions about this before I give you questions?
Do these values for normal and failure, they differ based on each patient, right?
Oh yeah, oh yeah. No, this is an example. Yeah, this is an example. There are also varying degrees of heart failure, and there's heart failure that can be well maintained with different types of medications. So there are a lot of changes that happen in heart failure, and one of the things that we will talk about that's treatment for heart failure, we'll actually get into when we talk about the kidneys, because one of the problems with heart failure is because of that lack of pressure. We'll get to this later in the unit, but just as a preview. When you can't generate that same amount of pressure, you start to have an increase in overall blood volume, and the kidneys can be used to help get rid of that excess blood volume. We'll talk about that when we get to our baroreceptors. But yes, it's going to fluctuate based on the degree and severity of that LV failure, and it will differ from patient to patient. The important thing is to note how your individual patient is progressing compared to their previous normal. All right, any other questions about that? Yeah.
Is that why the injection fraction goes down by so much because the volume's increasing and stroke volume is going down?
Yes, because you have that increase in end-diastolic volume, but because your stroke volume is decreasing, the overall fraction of the total amount of blood that's in there that's actually being injected is going to decrease. All right. Yeah, this is just to talk a little bit about a little bit of research. So we're good? Great. All right. Thank you very much. Appreciate that. All right, so this is one example of how far we've come in different types of research. It used to be when somebody ended up with heart failure, they needed to have a heart transplant. There really wasn't any other kind of treatment that could be done. When your heart stops working, you try to manage the symptoms, but you can't actually restore the ability of the heart itself. This was published, I think, 2014 in Circulation Research. It's talking about the long-term effects of adding a gene product, so SERCA2A, by adeno-associated viral vectors. Adeno-associated viral vectors don't cause disease in humans, so they're used frequently to deliver genes that can repair overall function. So for somebody who has different kinds of cardiac events, it has to do with, in this particular condition, it had to do with somebody who has a structurally normal heart. So they're not under conditions of heart failure. They have a structurally normal heart that seems to exhibit tachyarrhythmias, so elevated heart arrhythmias under conditions of exercise and stress, even though there isn't anything physically wrong with their heart. One of the benefits of the kinds of research, you're not going to be quizzed on this, just so you don't freak out, okay? This is just to introduce you guys to the stuff that's constantly happening. There are so many big advancements that can be made that a single dose of this particular, makeup resulted in a drastic drop in overall morbidity and mortality of people with this condition. And it seemed to be dose dependent. The highest dose, a single shot, protected people for months to a year. Up to 82% didn't have another cardiac event for the next 3 months, despite having visited hospitals and had other cardiac troubles throughout their daily lives. So the types of stuff that we're going to be talking about, we're going to talk about SERCA in just a little bit. You'll understand a little bit about why that would be particularly important and able to help maintain overall normal cycling of the function of the heart in terms of heart rate. But the benefits of the kinds of research that's being done is it allows us to be able to do non-invasive types of treatments. The last part I wanted to talk about was I wanted you guys to take a little bit of time to see if you can figure out which change in PD loop you would expect under each of these different conditions. So this one, I'm asking you about increased preload. A, B, or C, which do you think would be what you would expect to find in terms of how it would change if you increased just the preload. Preload only. Contractility, your inotropy stays the same, your afterload stays the same. The only thing that's changing in this instance is your preload. So where does that show up on that PE load?
Can you scroll down just a little? Thank you.
I wanted to make sure you guys can see the whole thing. There. Top one's A. All right, give me another 10 seconds. All right, 3, 2, 1, and we're done. All right, so here's the results we got. All right, we got lots of, everybody picked one of each. All right, so correct answer is anybody that put A. Your preload by definition is your end diastolic volume. So if you've increased only the preload without increasing anything else, the only thing that's moved is the right side of that red curve. So you can't see any of the gray curve under here, but you can see the black line that shows where the end diastolic volume used to be, around what, 110, 15, and then now it's up to about 150. Why is the end systolic volume the same? Looking at you, 503 people.
But is it because you still have the same initial like starting point and stretch valve?
Well, that, by definition, you do have the same initial starting point, but how are you able to get from a much bigger end diastolic volume to the same end systolic volume? How come your stroke volume is increased? How can that be?
Injection fraction.
Your injection fraction is going to be increased, right? Injection fraction is just your stroke volume divided by your end diastolic volume. It's the fraction of blood that's ejected based on the total amount that the blood can hold, or the heart can hold. So in this case, your ejection fraction's gone up because your stroke volume increased.
Is the atrial volume larger?
Nope. In this case, what we're looking at, if you've increased your preload, the reason you can still get down to that end systolic volume is because of something called the Frank-Starling mechanism. Now, just to reiterate, for those of you that did 503, we talked about an optimal length for cross-bridge cycling, an optimal overlap of actin and myosin filaments in that sarcomere. One thing I also mentioned at the time that I said we talk about now, which is today, is that cardiac muscle operates below that optimal length. That means that you can elevate the force of contraction if you have to accommodate a greater amount of volume coming back in.
What's that mechanism called?
Frank-Starling. Frank-Starling, it's not his first and last name. 2 last names. Because nobody in science ever works on anything completely by themselves. So, what's actually happening here is normal operating procedures indicate that you actually have a less than optimal overlap of actin and myosin in your cardiac muscle. Okay? So the force that's generated is a little bit lower than is capable of generating. The reason for that is to accommodate the changes in venous return. You will have circumstances that will cause your blood volume to go up. If you have more blood coming back to your heart, your heart needs to be able to not only accommodate changes in venous return, changes in the amount of blood that's coming back, but also be able to maintain blood flow to the periphery. All right, so Frank-Starling mechanism, basically by stretching that muscle cell, each of those sarcomeres are effectively pulling to their maximum overlap. And because of that, they can generate a little bit more contractile force.
How would pregnancy impact stress? Because blood volume is increased during pregnancy.
Yes, it is.
So what, in theory, what would the graph
So
look like?
So
Is it increasing that preload?
you will have that increase in overall preload because you are circulating a lot more volume. The other thing is, depending on overall, I guess, how far you are in pregnancy, the volume load that you've increased, it will also have an effect on your overall heart rate. That'll change as well to accommodate, to make sure that you're maintaining circulation, not only to the fetus, but also to yourself. So you will have that increase in preload, and this system will actually kick in as a result of that extra volume load. But it happens, it won't look exactly the same, but it will have that increase in end-diastolic volume, and you will have that compensatory increase in contractility to make sure that you're still supplying blood to the rest of the body in response to the increased volume that's coming in. But this can also happen under conditions of exercise. So people who exercise heavily, not only will you increase your heart rate, but you can also increase your stroke volume, specifically because you have a greater amount of blood that's coming back per unit time. And when we're talking about all of these, we're looking at changes in volume and changes in pressure, but your heart rate specifically in terms of stroke volume is how much is actually being pumped per unit time. So as your blood starts to flow a little faster when you're exercising, you have more coming back, you're going to increase the rate that's returning to the heart per unit of time. So that would be an example of that preload, but you can also have it under conditions of exercise where your stroke volume will increase, your heart rate, resting heart rate will actually go down because you've increased the force of contraction because your heart is a little bit bigger and a little bit stronger and can generate a larger stroke volume. So you'd see differences between somebody who's never exercised and somebody who exercises, either like marathon runners. You see differences in the PD loop in terms of the actual stroke volume and diastolic volume because of changes due to activity or inactivity.
And for an athlete, for somebody who's an athlete, say a marathon runner, and this is sort of a permanent change, and then what happens when they go back to a more sedentary lifestyle, or they're not a marathon runner, your kidneys just filter out, and you go back to that?
Yeah, your body's constantly in flux. So if you stop running altogether, you stop exercising altogether for whatever reason, your body will adjust to having that excess blood volume. The other thing is the extra muscles that you've developed in order to increase that contractility, they will eventually thin out too. So you can build muscle and you can lose muscle because your body's just cycling based on the needs. All right. Next question. You will find that these questions will get progressively easier because same answer choices. So if you missed the third one, I'm going to be very disappointed. All right, so now we're looking at increased afterload. Which one of these is going to deal with increased afterload? I'm also going to get mad if you check A. Because clearly that's a preload issue. All right, take a second and pick between B and C. Think about what afterload is. Remember, you're assuming that your preload is held constant and your contractility, your inotropy is held constant. All right, I'm going to stop you. Looks like we're doing pretty well. So, E. Increased afterload. By definition, what is afterload? It's the aortic pressure for our left ventricle. It is the pressure against which you have to overcome in order to get rid of the contents of that chamber. So, Pressure on the other side of the aortic valve is what you have to overcome. If you increase that pressure, what do you have to do to get that aortic valve open? You have to increase the pressure inside the left ventricle, right? So basically what we're looking at here is the difference between this point and this point. Okay? Because where I drew the lines, the bottom one corresponds to the gray curved black line. That's the point at which your aortic valve is going to open, which means you've generated sufficient amount of pressure inside the ventricle to overcome that aortic pressure. You can then open it up and eject your blood. If you increase the pressure that needs to be overcome, you have to increase the pressure inside the ventricle in order to get that valve open so that blood can be ejected. Anybody who's ever tried to lift up a single sheet of paper, or let's say a stone, like skipping stones. Anybody ever skip stones across water? Okay, lighter the stone, easier it is to skip. Okay, you pick up a huge boulder. First of all, you're not going to pick it up half as fast as you would normally for a small pebble, and it's not going to accomplish its goal. This is basically what's happening here. The muscle fiber is capable of contracting and therefore shortening in length at a speed concomitant with the weight it's trying to overcome. Picking up a piece of paper versus picking up a phys textbook, you can contract faster. The velocity of shortening is faster when you pick up a piece of paper than it is when you pick up a textbook. It's the same thing here. Because the velocity of the fiber shortening is going to be slower, now that you have a larger pressure on the other side to overcome, your stroke volume is going to decrease. Your ejection fraction is going to decrease because your stroke volume is lower, but the denominator of that equation, the end-diastolic volume, has stayed the same. So the fraction of blood that you are ejecting per heartbeat is now less. Under conditions of increased afterload, as long as you're keeping a constant preload, so that's here, constant preload and inner. Okay, that's important to note. All of these PD loop changes are taking a look at hypothetically what would happen if you only changed one of these three parameters. So, sorry, I hit the wrong button. All right, tell me what you think. What if you drop inotropy, but your afterload and your preload stay the same? Oh, good, I'm proud. Thank you. See, nobody is checking anywhere else. That's it. Your preload hasn't changed, so your end diastolic volume hasn't changed. That's what's happening here. That's the same, okay? Your contractility is the only thing that's changed. You haven't changed your overall afterload, which means that this point, this point is the same. Okay, so preload's the same, which is in blue, and that purple line is the afterload, showing that that's the same. The only thing that you've done is you've messed with your ability to generate that strength and contraction. Same preload, same afterload, contractility goes down, your stroke volume goes down. All right. And as I said before, since you lost inotropy, we're looking very specifically at this change. You have lost the ability to generate pressure at any given specific volume. All right, any questions on this wrap up of the material from last time? Yeah. Go ahead. Okay.
Those lines seem to be rotating around a fixed point. Is there a lower left ventricular pressure that's an absolute minimum that is rotating around besides zero?
What do you mean?
You see how the black line kind of looks like it's rotated when you go to the red line? Is there lower left ventricular pressure below which doesn't go besides zero?
Oh, yeah,
The
so,
y-intercept?
yeah, but so it stops before it ever gets to that y-intercept because you're never going to be able to eject all of the blood. So you're never actually going to get to that y-intercept because your heart is always going to have some residual blood. So it will continue down that trajectory in theory if you could actually vacate all the blood from the chamber.
So it looks like all of them were affecting systolic pressure. Is there any, in the left ventricle, is there any effects on actual blood pressure? in regards to this?
So, we're specifically looking at what's going on inside of the chamber itself. When you're talking about the overall change in blood pressure, you're talking about the mean arterial pressure, and that's what's measured outside. Okay, so when that'll actually come into play when you look at the difference between the stroke volume of the heart and the amount of heart blood that's actually getting out into circulation.
So you're
Right.
saying this doesn't really have an effect?
It
We
does,
discussed
it does, afterload especially. Because afterload by definition is a change in the aortic pressure, which is what's more mirrored on the arterial side. So what I'm saying is that the volumes that are changing here, the stroke volume, by definition, we're assuming that all of that is leaving out the aortic valve. What happens if it doesn't? What if it's leaving the heart and it's going somewhere else? Where else could it go? Okay, regurgitate. Right? Let's say you have a problem with your mitral valve. And when all that pressure is generated, in theory, you should be able to squeeze all that stroke volume out the aortic valve. But if you have a problem with the mitral valve, which is a pretty common problem in terms of valvular disease, if you get mitral regurgitation, you could squeeze out 75 mils of blood, but let's say 65 mils of that go into circulation and 10 mils of that goes back into the atrium because of incomplete closure. Okay? So that kind of stuff will come into play. We're looking specifically at what is happening inside of one particular chamber. All right. Any other questions?
I have a question.
Yes.
So is it more, do you see this all kind of together in like a heart issue, or are they more like isolated kind of things? Like do you just have decreased preload or increased preload, or can you have them all kind of?
Well, based on what we've talked about before, the first example, what do you think? They're all going to have a role. They might not every single one of them change, but the body is very resilient and it will compensate for changes. That's what we saw with the first one, where we saw the LV failure. This, in theory, is the same precipitating factor of LV failure, loss of entropy. But that other figure showed that it actually shifted over to the right. You had the same overall shape, but it shifted to the right because you had a compensatory increase in the diastolic volume. So yeah, that's why I specified that these figures are showing you just how one particular parameter change will affect the appearance of this loop. But under pathological conditions, you will have either one or more that are changed because of the pathology, and then you'll have one or more that is likely changed as part of the compensatory. Good question. All right. Okay, so we sort of talked a little bit about this already in terms of properties of cardiac muscle cells, specifically in terms of the length of the sarcomere that cardiac muscle is normally functioning at. This is a figure from the boron book. This one shows, really in the middle, you're looking at your myosin. They have that anti-parallel arrangement, so the heads are sticking out of either end. They look kind of like those mushrooms. And then your actin filaments are going to align anchored at the edges of the sarcomere, anchored at your Z-disc. Z-disc to Z-disc is going to be the length of your sarcomere. This is going to show your optimum overlap. Every single myosin head is in contact with an actin filament. The nebulin and the titin, those are things that we cover in 503. Titin gives it elastic properties. Nebulin helps to anchor it to the Z-disc, helps actin anchor to the Z-disc. Titin helps to anchor the M-band, which is where the myosin tails are anchored. You're not going to be tested on nebulin and titin. That's 503 territory. But for those of you that did 503, this should be pretty familiar. Cardiac muscle, I think I showed this figure in 503, but I omitted the last column. Now I'm going to show you the last column and show you how it differs from skeletal and smooth muscle. The biggest changes that we're going to look at here is that we have striations, We obviously have active actinomycin because every single one of these is going to have the actinomycin. It's under involuntary control. There's intrinsic control and there's extrinsic control. The Frank-Starling mechanism is an example of an intrinsic mechanism. It doesn't need to get a signal from any nerve or any hormone or anything else to change the overall stroke volume of the heart in response to changes in venous return. It's strictly a property of that cardiac muscle tissue itself. The similarity with striations is for your skeletal, but for most of what you're going to see here, you're going to see a lot of similarities with smooth. You have autonomic, right? And you see that in your smooth. That is not something that you would see in your skeletal muscle. You also have varicosities, so the overall structure is a little bit different. The biggest thing that is important to understand with these guys is that, let me see if it's on my list. It's not on my list, but I'm going to point out one other part. Troponin. It has the same troponin and tropomyosin system for regulating calcium that skeletal muscle does. The biggest difference is that source of calcium. That source of calcium is similar to smooth. So, as you can see, the cardiac muscle is going to be kind of a blend between skeletal and smooth. It uses the same calcium sensing mechanisms that you find in skeletal, but it requires extracellular calcium like smooth does. It uses striations, it has a sarcomere setup, but it also has these varicosities instead of active neuromuscular junction. All right, so looking at your cardiomyocyte structure, similar to what we see in skeletal muscle in terms of the striations, the biggest caveat that we have that's a little different is that we have these things called intercalated discs. So your cardiac cells have that striated function, they have that sarcomere function, but they function as a syncytium. They're capable of contracting all at the same time, which ideally is what we want, right? We don't want your heart to have every single muscle fiber stimulated individually, which is what we see in skeletal muscle, all right? Intercalated discs have very low resistance in between them. They are effectively gap junctions that electrically couple neighboring cells. It's the same thing that you would see in unitary smooth muscle. Okay, so unitary smooth muscle means the smooth muscle is capable of functioning as a unit. Electrical coupling of those cells, those neighboring muscle fibers, means that when one is stimulated, the electrical current inside of that cell can pass directly into the neighboring cell, so they can all get the stimulus to contract together, even if those neighboring cells did not directly receive that electrical stimulus. All right. Quick question about another feature of cardiac muscle altogether that makes it different. What do you think? For those of you that aren't sure, don't worry about the fact that in the top hat grade book it might say that you didn't get this right. It's because it's a word answer, and if you don't type the exact word in the exact way that I typed it, then you'll get it wrong even if you answered it correctly. That's why I don't grade. All right, I'm going to stop. Let's see what we got here. ATP, mitochondria. Very good. Let's see when I scroll up. Yay! Lots of people put in mitochondria. This one, that is what I was looking for. It's both. So, if you're going to get muscle contraction, you need not only, sorry, I keep hitting the wrong button. Not only do you need to have lots of mitochondria because you need lots of ATP. You cannot get contraction of muscle with cross-bridge cycling if you don't have ATP. ATP is required to progress through the entire cycling, cross-bridge cycling process. Without ATP and the hydrolysis of ATP, you don't get contraction. All right? So you need a lot of ATP. The most effective way to do that is to have a lot of mitochondria. Why does it also need to be highly vascularized? We're talking the equivalent of about 1 capillary per muscle fiber. That's a lot of vascular tissue. Lots of nutrients, lots of oxygen. Why? Lots of mitochondria, right? If you want aerobic respiration to generate all that ATP, you better supply it with sufficient amounts of oxygen to be able to run oxidative phosphorylation. Okay? So, if you want the heart to continue to contract over the course of your lifetime and have that lifetime last for decades, lots of vascularization, lots of mitochondria. And the vascular tissue is there to feed mitochondria to get enough ATP so you can have constant contraction. It's not like your heart takes a break. Well, it does get a break, but it's kind of a...
Just one break.
That's it. Okay. Cardiomyocyte structure. This on the figure A actually shows what it would look like if you had H&E staining, just to take a look at actual muscle fiber under a microscope. And then B is really showing a little bit about what is happening in between each of these muscle fibers. So there are two things that I want to point out here. Two things I want to point out. We have intercalated discs, and we have desmosomes. All right, the biggest difference here is that they're both going to be present. Let's see. This is the desmosome right there, and this is the intercalated disc, this whole thing here. The intercalated disc, as I said before, that's for electrical coupling. That means that your neighboring cardiac myocytes, so the cardiomyocytes is just heart muscle cells. Cardiomyocytes are electrically coupled with their neighbors, so that if you depolarize one, that depolarization will spread to every other muscle cell that is linked. Okay? That's a good thing, so that you can get all of the atrial cells to contract at the same time, and then all of the ventricular cells to contract at the same time. The desmosomes are mechanical coupling. These, anybody take cell biology? Did you talk anything about like how you mechanically create tissues and you link them together, intermediate filaments? We talked a little bit about it in 503. Desmosomes are the points for mechanical coupling between neighboring cells. It's so that if you are dealing with an organ that is going to be excessively stretched repeatedly, there needs to be something other than just a gap junction really between the neighboring cells to hold them together. Your desmosomes are there to mechanically provide support to link neighboring cells together so that all of that stretching doesn't rip your cells apart and cause them no longer to function as a system. That is another thing that is different from skeletal muscle. So even though striations are the same, the calcium sensing mechanism is the same, the overall structure, the intercalated disc to allow for electrical coupling, the varicosities, and the fact that extracellular calcium is necessary for the heart to function are more akin to smooth. So it's sort of a blending of the function of both.
You're talking a lot about the cardiac muscle in reference to the skeletal and smooth muscle. That was kind of a part 503. Should we still be?
You're not tested on skeletal or smooth. I'm just making relations because even if you haven't taken 503, you've probably been at least introduced to the different types of muscle in the body, so it's more for frame of reference. I'm not going to test you specifically on compare skeletal and cardiac, compare smooth and cardiac. But you should know the specifics of cardiac, which is
Right.
troponin and tropomyosin regulate calcium. Extracellular calcium is required. They're electrically coupled by intercalated discs, the desmosomes mechanically coupled. So any of the things I specifically said for cardiac is fair game, but I'm not going to ask you to compare and contrast with something you haven't had. All right, this one is just a close-up look. I think it's also from the Boron book, but it gives you a little bit of a closer view of what's happening in that intercalated disc. Specifically, that your gap junctions, that's for electrically coupling, right? And your desmosomes are for mechanically coupling, okay? Any questions on the function of these and the overall appearance of cardiac tissue so far? Now we're going to look at the ventricular muscle action potential. We will be looking at the other action potentials, but that will come on Thursday. Right now, we're just looking at ventricular action potential, ventricular muscle action potential. We have our 5 different phases, and different channels are going to be responsible for the changes in membrane voltage that you see at each one of these phases. The first thing that's going to happen, typically you're hovering around -85 to -95. That will be your resting membrane potential for cardiac tissue. It's more negative than the -70 that you kind of use as sort of a catch-all for most cells. Different types of cells with different functions are going to have varying resting membrane potentials based on what their overall intention is. In this case, we're looking at about -90. And in order to get that rapid depolarization, it's about 105 millivolts that you're going to change from about that, it's actually a -85 up to about +20 in this figure. That's 105 millivolt change during that depolarization part. So the peak is going to come all the way up to +20 millivolts. So on the y-axis, we're looking at the voltage itself in millivolts, and on the x-axis, we're looking at seconds. So we're looking at timing, okay? The first thing that happened, which is phase 0, that is the opening of your fast voltage-gated sodium channels. This is specific for ventricular muscle, okay? Not for all heart cells. We have different types of heart cells that have different types of action potentials. This is specific for ventricular muscle. Fast voltage-gated sodium channels are going to open, and then you will also have an opening of your L-type calcium channels. L-type calcium channels open a little bit more slowly. Just the kinetics of opening and closing is a little bit more slowly. And they, by that depolarization, will be triggered to open as well during that upshoot. You see a little bit of a dip once you've hit that peak, and that's because your potassium channels have now started to open. They are also voltage gated. Again, the kinetics are a little bit slower for causing them to open and close. But when your potassium channels open, because you have a lot of potassium inside the cell and not so much outside the cell, the gradient will be for potassium to leave the cell. Sodium has a much higher concentration, so does calcium outside the cell. So it's going to tend to enter. That's why when you open those channels, the entering positive charges will cause a depolarization. This slight repolarization is because as soon as those potassium channels start to open up, you still have calcium coming in, but now you have potassium leaving. Okay? And that initial opening, I guess, shakes the balance a little bit. This plateau is because those calcium channels are now in full force. The potassium channels are also open, so you have positive charges coming in by way of calcium. You have positive charges leaving by way of potassium. Your sodium channels are closed. They open fast, they inactivate, flow of sodium is done on that upshoot. Okay? At this point, you have calcium coming in and potassium leaving. So the voltage itself is going to roughly plateau and stay relatively constant during that point. As the calcium channels begin to close and you get more of those potassium channels opening, you're gonna start seeing less calcium coming in and a constant efflux of potassium. This is gonna be the repolarization side to allow resting membrane potential to come back down to, your action potential voltage to come back down toward resting membrane potential. The other thing that will happen is as those channels are starting to close, your potassium channels, once you drop below a certain voltage, they're going to close because it's a voltage trigger that causes them to open. So when you get below that trigger, that threshold, they'll start to close. There are G protein coupled inwardly rectifying potassium channels, the GIRK I mentioned last semester. Those help to maintain overall resting potential. By definition, an inwardly rectifying means that potassium specifically flows into the cell. It cannot flow out of that particular channel. Anytime we're talking about channels, the direction of flow is solely dictated by electrical gradient and chemical gradient together. Unless you're looking at a rectifying channel, which has a specific type of direction. That helps to kind of stabilize as the rest of those potassium channels are closing to get you back down to that resting membrane potential, which is at 0.4. So if you want to look at it from a figure standpoint, this one came from the Barnum-Levy. At 0, we see fast sodium channels, fast voltage-gated sodium channels that are going to open and inactivate rapidly. They're responsible for that upswing. The ITO, the I is for current, right? So back in physics, V equals IR, voltage equals current times resistance. That little I, that's your current. TO stands for transient outward. Okay, that actually has to do more with your T-type calcium channels versus your L-type. L-type calcium channels are doing the brunt of the work here. But you get a transient outward current that is going to show for potassium channels opening up. You get a slight repolarization. And then you have 3 different types of potassium channels that are all working excuse me, to balance out the calcium that's coming in. Phase 3, you've closed those calcium channels now and you're beginning that repolarization point. And potassium channels are responsible for maintaining that resting voltage. You will have a slight fluctuations in the way that these currents are happening because you have multiple different types of potassium channels, different types of calcium channels, all of which have slightly different kinetics. Okay, so each one of these, you see ITO, IK, IK1, all of these are different types of potassium currents. They're all under the global heading of voltage-gated potassium channels, but there are like 70 different types of potassium channels. So we're just going to talk about, this is not a cell class, so we're just going to focus on the group as a whole right now, but it is important that you understand that these different potassium currents are due to different types of potassium channels, all of which function to allow potassium to move across the membrane. They're voltage gated, but they activate and inactivate at different voltages. All right. All right, this figure here, I think I gave you this one ahead of time. It's got another part that's coming on the right. The reason for that is because we did just talk about the action potential itself, but we haven't talked about what's happening underneath. So what are we looking at down below? Current, right? These are all currents. We have sodium, calcium, and we have potassium. Which direction, above or below that dashed line, tells you that current is moving into the cell? Below. Okay? This means if we're below, that's in. Okay? If you are above, that's out. This is a standard readout. Whenever you're looking at current, if you're doing a patch clamp experiment and you are looking at current, any movement below that baseline shows that you have current flowing into the cell. Anything above that dashed line, which is that baseline, shows that you have current moving out of the cell. So you'll see the timing here gives you a little bit more of an indication of what's actually happening schematically. And in terms of its time course over the 200 to 300 milliseconds of that action potential, well, of the plateau. Typically, your action potential inside cardiac muscle can be anywhere from 250 to 400 or 500 milliseconds. And that's actually going to become very important in why your heart doesn't get tetanus. So, what's the first current? What's the first ion to flow? Sodium. It's quick. It's very quick. It opens, sodium comes in, it inactivates, sodium current's done, and the rest of it, nothing. No more sodium current after that initial upstroke. Okay? Depolarization because of sodium coming in. Now, if sodium's the first one, what does that mean for the voltage, the threshold at which it gets activated? It's more negative, right? It's the first one to activate. So, sodium is going to activate first. Your calcium and your potassium are both going to be activated by that depolarization, but they're going to happen at a slightly different rate. So calcium is going to follow this, I'll erase this in a second, but it's going to follow this trajectory where it comes in and then they start to close, right? And then it stays steady for the rest of the time. Okay, so you have the opening here, but this is closed. Okay, they've started to shut, you no longer have it coming in. You've reached that baseline, no more calcium is playing any kind of a role. That's why you see this, that plateau. It corresponds with what's happening with calcium. When you look at potassium, you see that it starts and it continues to stay elevated until after you've gotten down to that repolarization, when they finally start closing. These don't inactivate. Once they're open, they stay open and allow ions to flow until the overall voltage drops below its threshold, and then it will close. Okay, so your potassium is partly responsible for this plateau, and it is certainly responsible for the repolarization. Yeah.
For phase 4, you said that it says on that picture that sodium was coming in and out on the previous slide.
0, that's phase 0. Phase 4 is the resting. Here, see,
On the next slide, though, it's got like a channel of sodium coming in and out.
for phase 0.
For phase 4.
Oh, yeah, that's supposed to be.
Oh, so
So you will, so I should say that you actually have both of these. If you want to get technical, which I should because this figure is a little messy. I didn't want to confuse you, but you do have channels that allow stuff to leak across. We talked about that in silent grease. You have some ions that are capable of leaking across even at baseline voltages, but that balance is maintained. So you don't have any net movement, no net current moving, because that balance is going to be maintained by the sodium-potassium pump that's constantly working. So any leakage of sodium coming in and potassium leaking out is going to be pumped back out for sodium and pumped back in for potassium. So when we're looking at specifically the resting membrane potential, then we're talking mostly about like a net movement. You have a net efflux of that potassium that is responsible for keeping it at that value.
On the current picture, so to clarify, when the current is at 0, that means the channel is closed, or
That means there's no net current.
no net current?
Yeah, it doesn't mean that there's no current flowing, because you will have some moving in both directions. It just means that you don't have a net movement in one direction. In this case, this is only measuring from that baseline that you could have just equal amounts moving in and out that cancel each other out. It's when you have a net current moving in or a net current moving out that it starts to show up on this reality.
And you said calcium and potassium both like contributes to the plateau.
Yes, because calcium is coming in and potassium is leaving. And that's actually this section right here. So you can see that they're both open right here in this part. They're both open. until you see that you're starting to lose that calcium, and then potassium's the only one that's left.
So you said that inwardly rectifying potassium channels are why there's no hyperpolarization?
Yeah.
Okay.
So the reason that it comes back down and it sort of stays is because you still have your potassium channels that are allowing a constant leakage of potassium out of the cell, which means that it stays negative because you're always losing positive charges. But you have these inwardly rectifying potassium channels that also allow potassium selectively to come into the cell only. And that's why it tends to stabilize and doesn't really, doesn't move. So the last part I want to talk about here is just an overlap of what we're leading into next. On the top you have the ECG for the ventricle, so it doesn't show the peak wave because that's atrium. In the middle, that shows the action potential, that's the top on the left. And the bottom is what I'm going to lead into next time. This is for tension. That's the mechanical response, how the muscle responds to the electrical changes in the ventricle. All right, that'll do it, and I will see you guys on Thursday.